This video will discuss what and show what steam looks like coming from a electrically heated reactor. First we'll talk about what the reactor is. Next we'll show steam with 800 watts of heat and no cooling water. Steam with 800 watts of heat and 7 kilograms per hour of cooling water. Steam at 800 watts, 5.5 kilogram per hour cooling water. And then we'll discuss how much heat is lost in the exit hose. This is a copper steam generator constructed out of 1-inch copper tubing, a 2-inch copper tubing section. There's a 2000 watt 240 volt cartridge heater here that runs in the lower section. There's an inlet to allow water to be pumped in. Water is pumped by an FMI metering pump from a reservoir. Water or steam will flow up through here, leave this exit pipe, and flow down into a collection bucket. Temperature is monitored with 3 Type T thermocouples. One is located on the bottom here, one is located at the steam exit point, and one is located on the steam exit hose. Our laboratory is at 5,400 feet above sea level. The boiling point of water is 94.5. The reactor vessel has been filled with water, insulated, and placed inside a plexiglass shield. It's currently being operated with approximately 800 watts of electrical input and no flow. We can see from the meters it's 5.15 amps at 158 volts, 159 volts. Steam has been running for a while. We should be at steady state. See the steam condensing on the plexiglass. What we have now is the same input power, 5.17 amps, 159 volts, with 7 kilograms per hour of water flowing. The water comes out of the reservoir at 22 degrees C, so it's heated to boiling, and there's enough energy to make a little bit of steam. You can look at the bucket here, you can see it bubbling. Try to show the steam. The steam's a little hard to see. We'll drain the hose because there's quite a bit of water coming out as well. You'll see some steam and then a little geyser. Do that again, you can see the steam. Plexiglass much less steam than before, and it starts to fill up with water, and then it percolates the water out. This has been running for some time, so it's at steady state. And again, you can see the amount of steam. A little hard to see unless you're right against the black. I'm not sure you'll be able to hear the gurgling, but there's a pretty noticeable gurgling inside the pipe, and the longer I hold it this way, the more gurgling I get. And as we saw before, if I hold it long enough, I'll get the percolator effect. There we go. Let me summarize what we've seen. In the first test, 800 watts with no flow. There was significant visible steam. We saw loud bubbling in the bucket. Very little water condensed in the black outlet tube. The second test was 800 watts with 7 kilograms per hour of flow. In that case, we saw very little visible steam. We saw that there was some steam. There was a little bit of bubbling in the bucket, and the percolator effect happened very quickly. The final test was with 5.5 kilograms per hour of flow. There was a little bit more visible steam, and the percolator effect happened, but it took quite a while before you could see it. This LabVIEW chart shows the thermocouples data is recorded, sampled once every 10 seconds for the 3 thermocouples. The white trace is the thermocouple on the bottom of the tube underneath the heater. The red trace is the temperature at the steam exit point, and the green is the steam pipe, the black pipe. This point here is where we turn the flow on. So this was the 800 watts with no flow. See, these were both at the boiling point in the 94.5 degrees C range. We also see that this is about 10 degrees less, so from that we'll be able to calculate the heat loss through the black pipe. You can see when we turn the flow on, we got a little 1 degree C drop in temperature down at the bottom, so that water wasn't being boiled. And finally, we look at the heat loss through the hose. We estimate the thermal conductivity of the hose on the order of 0.2 watts per meter Kelvin. As we said before, delta T was approximately 10 Kelvin. The inside diameter was 9.5, so the radius is half that. The outside diameter was 16 millimeters. This is the formula for heat loss through a hose, and we end up with something on the order of 25 watts per meter of heat loss through the rubber hose.